Hello, my name is G. Saranraj and I'm a PhD student under Dr. Anirban Guha at the University of Dundee. The title of the work we are presenting today is Energy Transfer in Resonant and Near Resonant Internal Wave Triads for Non-Uniform Stratifications, Part 2, Bounded Domain with Varying Topography. One of the reasons we study internal gravity waves is because of its association with meridional overturning circulation, or MOC. MOC is an important part of the Earth's climate. For example, it transfers a significant amount of heat from the equator to the poles. This MOC is sustained by the internal gravity waves mechanical energy. Internal gravity waves breakdown and eventual mixing and turbulence increases the diffusion throughout the ocean. This increased diffusion helps in upwelling the formation, upwelling the deep water which is formed in the poles. The breakdown of internal gravity waves occurs at very small length scales, such as in the order of centimeters. However, internal gravity waves in the ocean are formed or forced at very large length scales. So the energy has to cascade from very large length scales to the small length scales. This one of the mechanisms which makes this cascade possible is wave-wave interactions. In this study, we focus on wave-wave interactions in the presence of a slowly varying bathymetry. The wave number of the wave or the wave number of the wave is much larger than the wave number of the topography or the characteristic wave number of the topography. Uh, we also focus on parameter regime in which the topography does not interact or scatter the waves involved in the triad interaction. The figure 1b also shows the typical stratification profile we use in this study. The wave-wave interactions we focus in this study are triads and self-interactions. They are weakly nonlinear resonant processes. For three waves to form a triad, the angular frequency condition and the horizontal wave number condition, according to equation 1, has to be satisfied. In a similar way, resonant interaction also for two waves to be involved in a resonant interaction, equation 2 has to be satisfied. The vertical wave number condition in the bounded domain is slightly more involved, and it is not like as straightforward as for example, the horizontal wave number condition given in the equation 1. Moreover, another thing is important thing to realize here is that all the waves should satisfy the linear dispersion relation according to the system. The buoyancy frequency profile in this study is assumed to vary in the z direction. The buoyancy frequency is always taken to be constant near the surface of the topography or near the full depth of the ocean, and it is assumed to have a strong increase near the surface, a strong but localized increase near the surface to model the typical picnoclines in the ocean. So this type of a strong increase is modeled using a Gaussian function in the stratification profile as shown in equation 3. Here ZC and WP represents the depth and the width of the picnocline or the Gaussian mountain, and the Nmax represents the strength of the stratification increase near the surface. So such profiles have also been used in other studies. Since we are considering large amplitude topography, we convert the domain, uh, we use terrain following coordinates. That is, we convert the domain from xz, usual xz coordinates to an x eta coordinates, where eta is defined as given in equation 4. This would make the domain from a deformed shape as shown in figure 3a, a typical topography, to a domain which is rectangular in shape, which makes it easier to deal with the boundary conditions. This is done by using the transformation eta equal to minus z by h of x as shown in equation 4. So the governing equations we use are the inviscid incompressible 2D Navier-Stokes equation in the F plane. The equations shown in phi a, phi b, phi c are in terrain following coordinates by using the chain rules of partial differentiation. So here psi b and v are stream function, buoyancy and meridional velocity in the terrain following coordinates respectively, and f is the Coriolis frequency. Instead of solving the full problem using a DNS or full numerical simulation, we use multiple scale analysis. Uh, because of this, we assume our three fundamental flow variables psi b and v as a product of fastly varying phase and slowly varying amplitude. Here epsilon x and epsilon t are small parameters denoting the slow variation in x and t, and aj is the complex amplitude that varies both in x and t. And here phi as given in equation 7a and 7b or 7c uh, represents the vertical structure of the wave or gives the vertical structure of the wave. Now we substitute this psi bv the main governing equations phi A, phi B, and phi C, and arrive at an eigenvalue problem given by equation 8. This eigenvalue problem actually has countably infinite solutions, and the superscript n in the equation represents that it is the nth solution. Phi n is the vertical shape of the stream function of the wave, and mathcal k is the nth eigenvalue. Both of them are actually functions of h. That is, if h varies, uh, phi n also changes, and also the eigenvalue changes. This is because n square becomes a function of x in x eta coordinates if n square is a function of z in the xz coordinates. This is also shown in figure 4, where stratification profiles are drawn at the base of the mountain and at the top of the mountain. The effective stratification profile felt by the mode is shown in figure 4b, where in the stratification profile at the top of the mountain has a larger width of the pycnocline and also a larger depth of the pycnocline. Here in figure 5, we actually see the variation of the non-dimensionalized eigenvalue with h. Here we can see that different eigenvalues, that is for different n values, the function evolves differently as h changes. The parameters used in generating this graph is also given in this slide. So lower modes' eigenvalues are all different functions of h. As a consequence, the horizontal triad condition given by k1 plus k2 plus k3 equal to 0, if even if it is satisfied at a particular h, it may not be satisfied at all h, because each eigenvalue appears to be a different function of h. Hence, triad interactions that do not follow the conditions where all waves are the same modes for their particular angular frequency, they may get detuned as h changes. As seen from the previous slide, since different eigenvalues can vary differently with h, even though triad condition is satisfied at a single location, it may not be satisfied for all h. This is shown in figure 6, where we consider some triad interactions which are satisfied near h or nearly satisfied near h, but they get heavily detuned as the h increases. The definition of delta k is given in the slide. The parameters also used in generating these triad interactions are also given in the slide. Hence, we can conclude that delta k or the detuning can be quite sensitive as h is varied. So even though a triad is satisfied at a particular h, it need not be satisfied in all locations if the stratification is actually varying in z direction in xz coordinates. So an important point also to realize is that for a constant n, the eigenvalue does not change in x direction even if h varies. Hence, if for a constant stratification, if the triad condition is satisfied at a single h value or a single domain depth, it will be satisfied at all locations. Even in non-uniform stratifications in n, if triads such that the if triads such that a equal to b equal to c, which means that the mode numbers of all the waves involved in the triad are the same, then detuning was still observed to be considerably lesser. Now we move on to the amplitude evolution equations, which we get at order epsilon square after applying the solvability condition. So these are the two equations, amplitude evolution equations for a self-interaction process. Here, wave 1 is considered as the parent wave, and here delta ks is the detuning for a self-interaction process, and cj is the group speed, and capital N or N is the nonlinear coupling coefficients, which decides the rate of energy transfer. In figure 7, variation of the nonlinear coupling coefficients with H is shown for several different self-interactions. It can be seen that the nonlinear coupling coefficients can also be quite sensitive to the changes in H. Hence, the energy transfer will also be quite sensitive to changes in H. Moreover, even though the mode numbers involved in the self-interactions are different, the detuning was still observed to be quite low for the given change in H. This is because the eigenvalues evolved quite similarly, even though they are the eigenvalues of different modes. As a summary, we consider three waves with horizontal wave number k1, k2, k3 forming a triad. Here, ABC represents the mode number. It was observed that if in uniform stratification, if the triad condition is satisfied at a single h, then it will be satisfied even as h is varied. However, in non-uniform stratification, if the condition A equal to B equal to C is not satisfied, then as H is varied, detuning may occur. or detuning may be introduced in the triad. In triad and self interactions, the nonlinear coupling coefficients can also be quite sensitive as H is varied.